Hello everyone, you're welcome to my channel. My name is Anch, and in this video we're going to solve this problem right here. So we suppose that f is a differentiable real function such that this inequality holds, okay, for all x, and then f evaluated at 0 is 0. Now what's the largest possible value of x? Good. So I found this question from one of blackpenredpen's video. At the end of the video, if you posted the question, though it's been a long time video, but I just found it recently, and the solution that I made for the video is really interesting, and in fact if you have yours, please don't forget to put it in the comment section below. And as you watch, if you enjoyed the video, please don't forget to subscribe to my channel and share the video with your friends. Right? Okay, let's continue. So the first thing I'd like to do, of course, is to just write solution, whether I know what to do or not. All right, just write solution. Okay, great. So the next thing is to think about the question. So we have to find the largest possible value of f evaluated at 1, okay, given that this inequality holds. So I'm going to put down the inequality, but I'm going to rewrite it in this way. So that I'm going to write the derivative first plus f evaluated at x. Good. This is less than or equal to 1. Okay, then the next thing is, well, what I'd like to do here is to multiply both sides, that is multiply through by e to the x. Okay, and you may say, well, where is that from? Well, if you think about this inequality as a first order differential equation, okay, but this is an inequality, okay, you may think about the integrating factor, which will may be e to the power of x. Okay, so you just multiply that. Then we multiply the first. We will multiply the left hand side. This will just be e to the x. While the order of the inequality will not be reversed. It will stay because this function right here is positive for every real number. Okay, that is for every x. So e to the x times the derivative plus e to the x times the function. This is e to the x. Then the order stays, that is just e to the x on the right hand side. Okay, the next thing I'd like to do is to rewrite this left hand side. This is just e to the x times f of x. So you notice that when we differentiate this left hand side, that is when we take the derivative of this product, we'll just have this left hand side. This is e to the x times the derivative of f plus f times the derivative of e to the x. But when you differentiate e to the x, it stays the same, right? Good. Okay, the next thing would be to move this term to the left hand side. I just want to clean things up on the right. Okay, so we move that term to the left. Notice what we have. This is going to be the same thing as e to the power of x times f of x, okay, minus e to the power of x. Then the derivative covers that. This is less than or equal to 0. Well, you may say, why is that? Well, this right here, using the fact that the differential operator, okay, is linear, that is the derivative of the difference is the difference of the derivative. So I'm able to put that in. And this doesn't change because when we differentiate the exponential function, it stays the same. Okay, so what I'll do now is to integrate both sides from 0 to 1. I'm picking 0 because the initial condition is given, and I'm picking 1 because it is simple to think about 1 right here. So we integrate the left hand side from 0 to 1 over the x variable, okay, and then we also integrate the right hand side from 0 to 1 over the x variable. Good. Okay, so on the left hand side we have this term right here, so you take note of that. So that is going to be the derivative of e to the x times f of x, right, minus e to the x. Good, that was differentiated. Okay, this is less than or equal to, well, the order will still stay, because this right here is like is at most 0. Good. Okay, so let's integrate that. When you integrate the derivative, okay, by the fundamental theorem of calculus, we're going to have to evaluate this inside function from 0 to 1. So we evaluate e to the x times f of x minus e to the x, okay, evaluate that from 0 to 1. Good. Without the derivative because the integral is taking care of that. Well, we integrate 0 over the indefinite interval, we're just going to have 0. Okay, so this is at most 0. Good. So we integrate, we evaluate this term, this function at 1. Well, this will become e to the power of x times f evaluated at e to the power of x is 1 times f evaluated at 1. All right, good. Then minus e to the power of 1. That's what we get when we evaluate it at 1. Then we subtract, we evaluate this thing at 0. So you notice that if evaluated at 0 from the initial condition is given at 0. So that means we're going to subtract. Well, when we evaluate it at 0, we're going to have 0. Then minus negative of, that will be plus. We evaluate this term at 0, that is just going to be 1. This is equal to 0. So we clean things up a little bit. All right, good. So this is going to be e. On the right hand side, this will be less than or equal to e, then minus 1. That is e to the power of, e times f evaluated at 1 is less than or equal to that. So making f of 1 to stand alone on one side, this should be less than or equal to, well, that will be 1 minus 1 over e. So yeah, this f evaluated at 1 is less than or equal to that. It is at most 1 minus 1 over e, right? It is at most that. So the largest possible value will be when the equality sign holds. So you now say that, I'm going to put it in the statement, that therefore the largest possible value of if evaluated at 1 is, now that is, let me just put it as an equation, f of 1 equals to 1 minus that. Okay, so that's the solution to the problem. All right, I hope you enjoyed the video. Please don't forget to share the video with your friends, subscribe to my channel, and continue from my next video.